Before starting our discussion of harmonic measure, we need to review some essential properties of harmonic functions. So the most important and characteristic property of harmonic functions is the mean value property. So this says if we have a harmonic function, some domain omega, then for any ball B contained inside omega, if we take the average of u along the boundary of the ball B, this is equal to the value of u at the center of the ball. And the same thing happens if we take the average of u with respect to Lebesgue measure inside the whole ball. Okay, so notation here, so sigma represents surface measure. So by default, if I'm working in RD plus 1, for example, then sigma is going to be some normalizing constant times Hausdorff measure, where this normalizing constant is so that if I restrict sigma to RD, I just get Lebesgue measure back. Okay, so the proof of this is not too difficult, and it's in standard PDE textbooks, like in Evans' PDE book, and it's just an application of Green's identity. What's a little trickier to show is that the mean value property actually characterizes harmonicity. So if you have a locally integrable function in U and it's the average of U inside any ball equals U evaluated at the center, then U is a harmonic function. So we won't prove this, but we'll take this fact for granted. The next important feature of harmonic functions is the maximum principle. So suppose we have a harmonic function defined in some connected open set omega, and it attains its supremum in omega. Then this implies U must be constant. If additionally we know that U is continuous up to the boundary of omega and the domain omega is bounded, then the supremum of U in omega is actually the supremum of U on the boundary. So we'll just prove the first part of this theorem, and then the second part we'll leave as an exercise. So let's consider a point x in omega where U of x is equal to the supremum of U in omega. Now, because omega is open, that implies that we can find a open ball around x that's contained inside omega. Okay, now let's suppose that we could find a point inside this ball where U was strictly less than the supremum of U. Okay, well, by continuity, that implies that there's a small ball around this one where U is strictly less than the supremum. So that implies that if we take the average of U inside this ball, so let's say this ball is B, this is strictly less than the supremum of U in omega. But this, we're assuming, is equal to U of x, but by the mean value principle, this is equal to U of x as well. Okay, and now we get a contradiction because now U of x is strictly less than U of x. So what we've shown now is that for any point x where U of x equals the supremum, there is a ball around it where every other point in the ball, the function U must also equal the supremum, since there can be no points in the ball less than the supremum. So thus, if we look at the set of x such that U of x is equal to the supremum of U in omega, now because U is a continuous function, this is going to be a closed subset relative to the domain omega, okay? But what we've shown here is that every ball x inside this set is contained inside a ball where the function U is also equal to the supremum, which means that all those points inside that ball is also contained inside this set. But this means that this set is also open. And the only way that a connected metric space can have a closed and open subset of itself is if that subset is equal to the whole space. And so that implies, in fact, that this is equal to omega, and therefore the function U is constant. So recall when I first defined harmonic functions, I assumed a priori that they were twice differentiable. But it turns out that if you have a harmonic function in the domain omega, then it's smooth. It has infinitely many derivatives. And moreover, there are nice estimates on the derivatives. If we have a ball, Bxr, contained in omega, and we have a multi-index alpha, then if we take the alpha partial derivative of U, then this is at most some constant depending on the dimension of the ambient space times the order of the derivative we're taking, so the length of the multi-index alpha, times r to the minus alpha times the average of U inside this ball. So let me sketch some ideas about how to prove these different facts. So I'm going to fix a function phi supported in the unit ball that's radially symmetric around the origin. So phi is radially symmetric. And support of phi is contained inside the unit ball. So I'll just call that boldface B. And I'm also going to assume that the integral of phi is equal to 1. Okay, and I'll also assume that's non-negative. Okay, now I'm going to define a function phi r of x, which is equal to r to the minus n times phi of x r. Okay, so what does this transformation do? So the way to picture this is, let's say this is the graph of my original function phi. If I pick a small value of r, the graph of the resulting function is going to look like this. It's going to be a lot steeper and more concentrated around the origin, but in such a way that you can show by change of variables that the integral of this function is unchanged. So the integral of phi r is equal to 1. All right. Moreover, the support now of phi r is now contained inside the ball center at 0 of radius r. So I'll leave these facts for you to check. Okay, so now let's suppose we have a point x in omega, so that its distance to the complement of omega is bigger than r. Okay, so if we look at u convolved with phi r of x, so notice that this is the same thing as the integral of u of y times phi r of y minus x dy. Okay, why does this integral make sense? Because u is only defined in the domain omega, so potentially this could be integrating over places where u is undefined. But notice that we picked a point x so that its distance from the complement of omega is bigger than r, and this function phi r of y minus x. So this is essentially the function phi r translated, so now it's centered on x. So now its support is going to be contained inside the ball center at x of radius r, which by assumption is contained inside omega. So this integral makes sense. Now, because of the radial symmetry of phi r and the fact that the integral of phi r is equal to 1, this phi r of y minus x, this is going to be a radially symmetric function around the point x. And so you can show by a computation using, for example, polar coordinates and the fact that polar coordinates around the point x and the fact that we have the mean value property for the function u, so its integral on spherical shells around x is equal to u of x. This integral is actually just equal to u at x. Okay, so in particular, we have that u of x, for points x, distance greater than r away from the complement of omega, u of x is equal to the convolution of itself with a smooth function. But when you convolve a function with a smooth function, that function is again smooth. And this implies that u is smooth for all points distance r away from the boundary. But letting r go to 0, this implies that u is actually smooth everywhere. Okay, so how do we get this Cauchy estimate here? So if we look at the, so I'm just going to clear up some room here. So if we look at the alpha derivative of u at x, okay, so u of x is equal to u convolved with phi r of x, assuming that x is distance r away from the boundary. And then I can just pass the derivative on to the smooth function phi r of x. Okay, now you can show that this is at most the L1 norm of u inside the ball center x of radius r times the L infinity norm of the alpha derivative of phi r of x inside the ball center x of radius r. Okay, now recall that phi was some radially symmetric smooth function in the unit ball. So its infinity norm inside the unit ball is just some fixed number. But then when we take phi r, okay, its infinity norm is r to the minus n times the infinity norm of phi. So it's going to be some constant times r to the minus n. And notice that each time I take a derivative of phi r, I'm going to pull out a 1 over r from phi. So that means that if I take the alpha derivative of phi r, its infinity norm is actually going to be equal to, so I'll just erase that. This is equal to r to the minus alpha minus n times the infinity norm of phi, which will just be some fixed constant. And now I have r to the minus n here, So r to the minus n, if the dimension of my space is n, r to the minus n is comparable to the it's comparable to the measure of the ball bxr, right? So that means that this quantity here is effectively this one. R to the minus n times the L1 integral of u in this ball is the same thing essentially as taking the average, or they're comparable. And so thus this quantity here is comparable to this one up here, and that finishes the proof. So harmonic functions are actually even better than smooth. They are real analytic, and I won't prove this result. I'll end up depending on it a bit later. But the proof is not too difficult, and you can look in Evans' partial differential equations book for a proof. Harmonic functions also have some nice limiting properties. So let's say you have a sequence of harmonic functions defined on the domain omega that converge uniformly to some other function u on omega. Then the function u is harmonic. Okay, and the reason why is because, recall that I said earlier that a locally integrable function is harmonic if it satisfies the mean value property. So if you have a ball contained in omega, then if u is converging uniformly on the domain omega, then it's converging uniformly on this ball. So that means that these integrals, so the integral of u is equal to the limit of the integral of the uj's, and since those functions are all harmonic, this just equal to the limit of uj evaluated at the center of the ball. Since uj converges to u, this is equal to u at x. Okay, so thus the function u satisfies the mean value property in the domain omega, and hence it must be harmonic as well. We also have nice compactness properties for harmonic functions. So if we have a sequence of uniformly bounded harmonic functions in the domain omega, we can pass to a subsequence that converges uniformly on compact subsets of omega. And this follows just from the Cauchy estimates, because if we have a uniformly bounded sequence of harmonic functions on some open set, then that means inside every ball, they are uniformly bounded. And then using Cauchy estimates, you can show that the first derivative is uniformly bounded on each ball. So that means that these functions uj are uniformly Lipschitz inside each ball contained inside your domain. And that implies that they form a sort of locally equicontinuous family of functions. And thus we can use Arzela-Ascoli to prove that we can pass to a subsequence that they converge uniformly on compact subsets of omega. And as the previous theorem says, this subsequence will converge to a harmonic function. The final result we'll discuss is Harnack's principle. So given an open set omega and a positive harmonic function u in omega, suppose we have a ball B such that 4 times B is contained in omega. Then, for any pair of points x and y and b, the value of u at x is comparable to the value of u at y. So in other words, all values of u inside this ball are comparable to each other. So every value of u is no more than some fixed multiple times any other value of u inside this ball, where the implicit constant in this inequality only depends on the dimension of the ambient space. So it's independent of the ball that we pick, the domain we're working with, and the positive harmonic function. So let's go over the proofs. So let's suppose that we have a positive harmonic function u in some domain omega, and we have some ball b here such that 4 times b is contained in omega. And let's suppose we have a pair of points x and y in omega. So now our goal is to show that the value of u at x is no more than some multiple of u evaluated at y. So recall that by the mean value property, the value of u at the point x is equal to the average inside any ball center at x. So in particular, it's equal to the average of u inside the ball center at x of radius rb, where rb is the radius of this ball b. Okay. Now, because x and y are both inside the ball b, that means that the ball center at x of radius rb will be contained in the ball center at y of radius 3rb. Okay, so this implies that the average of u inside this ball is at most some constant times the average inside this ball. So let's see how this works. So let's look at the average of u inside the ball center x of radius rb. All right, so if we write out what this is the same thing as taking 1 over Lebesgue measure of the ball x rb times the integral of the ball center x of radius rb of u. But this ball here is contained inside the ball by 3rb. And because the function u is positive, that means that this integral is at most 1 over the measure of the ball bxrb times the integral over by 3rb of u. Now, if we multiply and divide by the volume of this ball, okay, we get that this is the same thing as the volume of ball y3rb. So we multiply and then we divide, but that's the same thing as just taking the average of u inside this ball. But then this here, now we have two balls where one ball is just 3 times the radius of the other, which means that their volumes are just multiples of each other. In fact, the ratio between the volumes of these two balls is just equal to 3 to the n, since recall we're working in Rn. And then again, by the mean value, so notice now by the mean value property, this first integral here is equal to u at x, and this last integral here is equal to u at y. So thus, in fact, we have u of x is always at most 3 to the n times u of y. And notice that we could do all this because all these balls are contained inside omega. And the reason why that is because since x and y are inside omega, one can show, because x and y are inside the ball B, one can show that each of these balls that we're working with, bxrb and by3rb, they're all contained inside 4b, and this is contained inside omega. And that finishes the proof.